All right, hey everybody, AB Calc. This is section 5.6, day number 2. We're going to do a little long division today. To start, let's remind ourselves of, well, how to do long division. So let's take, let's say 13, and divide it into, I don't know, let's go 4,027. Okay, let's remind ourselves how we do this thing called long division. So 13 doesn't go into 4, but 13 goes into 40. It goes in 3 times. We multiply through. 3 times 13 is 39. Do a little subtraction. We get a 1. Now 13 doesn't go into 1. And 13 doesn't go into 12, but 13 does go into 127. Goes in almost 10 times. Okay, actually goes in 9 times. So I'm going to plug in 0 and a 9 for 9 times. So 9 times 13 is 90. 90 plus 27 is 117. Okay, we're going to subtract. We get a remainder of 10. Now 13 doesn't go into 10, so 4,027 divided by 13 is equal to 309 and 10/13. Okay, so that's how we do some long division with, numerical expressions, right, or numbers. Now let's do it with some polynomials. First, let's talk about how you know you're going to be working with integration by long division. First of all, you'll have polynomial expressions in the numerator and denominator creating rational functions. Okay, so you can see here in examples 1, 2, and 3, you got rational functions in all cases, right? Polynomial, numerator, and denominator. Okay, so that's indicator number 1. Right, number 1, dealing with a rational function. With numerator and denominator polynomials. Okay, indicator number 2 is that the degree of the numerator is, oh gosh, I'm running out of space, is greater than or equal to the degree of the denominator. Okay, so let's talk about that. Find the leading term. There's only one term here. It's x to the first. Degree is 1. Degree of the bottom, leading term is x to the first. So the degree and the numerator denominator are the same. Look at number 2. Degree of the numerator is 2. Degree of the denominator is 1. Degree of the numerator is greater than or equal to the degree of the denominator. Likewise, down here in example 3, degree in numerator is 3, degree in the denominator is 2. Say that fast, that's not easy to do. Okay, so what I'm going to do is consider this basic elementary example over here. Is 4,027 divided by 13 can be rewritten in this form. Okay, so in the same way, I'm going to put x plus 5 on the outside, and I'm going to put a 2x plus 0. The 0 is really just a placeholder right there. So I'm going to do a little division here. So I always work with the leading term, right? The leading term. So I don't really care about the 5 until I multiply through. So I'm going to take x and multiply it by a 2 to get a 2x. So 2 times x is 2x, and 2 times 5 is 10. Okay, so now I'm going to subtract. 2x is reduced as planned. 0 minus 10 is a negative 10. Thus, this integral will be equivalent to the integral of 2 minus 10 over x plus 5. Okay, now when integrating this, I'm going to actually split this into 2 integrals using the sum and difference rules. And I'm actually going to bring that 10 out in front. Make this the integral of 1 over x plus 5 dx. Okay, so relatively easy in this first integral. I'll get 2x. I'm not going to add a constant of integration yet. I'm just going to add it at the very end. Minus 10. And now the integral of 1 over x plus 5 is actually equal to the natural log of the absolute value of x plus 5 plus c. And there you have it. It's integration by long division. Now, I have skipped a little bit here. This might require you, if your knowledge is kind of basic, to use a u sub. So I can work that out over on the side here real quick. I'm going to set u equal to x plus 5. So du is going to be equal to 1 dx. And thus I can adapt this, right, this original integral, 1 over x plus 5, to be equal to the integral of 1 over u du, which of course comes out to be the ln of the absolute value of u plus c, and u, of course, is equal to x plus 5. And I just bring that negative 10 along with it. So as you get better at u subs, it'll make all the difference in the world. Okay. So there you go. There's your integral. How did that turn red? That's interesting. Of 2x over x plus 5 with respect to x. All right, let's look at the second example here. Second example, I'm going to take x plus 2 and divide it into x squared minus x minus 5. Now x goes into x squared x times. X times x is x squared. X times 2 is a positive 2x. With long division, we always subtract. X squareds reduce. Negative x minus 2x is a negative 3x. I drop down my negative 5 to match terms. And x goes into negative 3x, negative 3 times. Multiply through again. I get a negative 3x minus a 6. And I subtract. It looks like I'll have a remainder. That remainder will be a 1. Therefore, the integral from 1 to 2 of x squared minus x minus 5 over x plus 2, all that stuff, is going to be x minus 3 plus 1 over x plus 2. Okay, this can also be written as 3 integrals if we wanted it to be, but I'm just going to keep it all together as is. And I'm going to write this as x squared over 2 minus 3x. In a very similar way, I could use a u sub, or I could write this as the ln of x, the ln of the absolute value of x plus 2. Now I don't need plus c because we can see this is a definite integral with its limits top and bottom, so I'm going to evaluate from 1 to 2. Okay, at this point, because my values for 1 and 2 would make the natural log, a natural log of positive 4 and a natural log of 3. I don't need the absolute values. I'll just leave it just because. So I'm going to take and evaluate at 2. That'll be 4 over 2 minus 6 plus ln of 4 minus, that'll be 1 over 2 minus 3 plus ln of 3. And we can kind of squeeze things together here, make it a little bit cleaner. This would be negative 4 plus ln of 4 minus, what would that be? Negative 5 halves plus ln of 3, which would be, what would that be, 8 halves, so positive 3 halves. Now, ln of 4 minus ln of 3 is equivalent to ln of 4/3. And that would be our answer, guys. There you have it. Okay, a little long division in the third one. Let's do it. Okay, so as I look at the numerator, I can see there's a missing term. Denominator is not missing any terms. So I'm going to put a placeholder of 0 in for that missing term. goodness, get some skills, and oh my gosh, that was terrible. Alright, that's about as good as I can do right now. X cubed plus x squared plus 0x minus 1. I always put a placeholder in there just to keep things straight. X squared times x is x cubed, so I get x times x squared is x cubed. X times x is x squared. Ooh, that's going to reduce nicely. Plus 2x. Subtract all of that. Okay, it looks like the x cubes, x squareds, they reduce. I get negative 2x, and I drop down to negative 1. And, of course, x squared doesn't go into that. Okay, so I'm going to leave that as is. Therefore, this will be the integral of x minus, okay, so this is one way to write it. Right, 2x plus 1 over x squared plus x plus 2 dx. Okay, or I could write, plus and then put a minus here and a minus here. Okay, but I'm not going to do that. Okay, now, this is interesting. You might think, how am I supposed to integrate the second part? Well, this actually lines up perfectly. What's the derivative of x squared plus x plus 2? Well, it's 2x plus 1. Perfect. Perfect. It lines up nicely for a u substitution. So I'm going to write this as two integrals. The integral of x dx minus the integral of 2x plus 1 over x squared plus x plus 2. Okay, so the first integral will be x squared over 2 minus, now I'm going to do a side u sub work here. So I'm going to write u equals x squared plus x plus 2. So that means du is going to equal 2x plus 1 dx. Okay, it's going to be a nice, perfect substitution. I'm going to actually rewrite this in integral form. This will be the integral of 1 over u du. All right, you can see du replaces 2x plus 1 dx, which is numerator and, of course, the dx. And u replaces x squared plus x plus 2, which will give us 1 over u du. Okay, so I would get x squared over 2 minus the natural log of the absolute value of u, which is x squared plus x plus 2. That is an awesome example of how to use both the substitution technique as well as just some long division work. Okay, let's look at the next slide. All right, number 4. You can see in number 4, we've got, again, our first kind of checkpoint is, do I have polynomial top and bottom forming a rational expression? Yes, I do. Is the numerator's degree greater than or equal to the denominator? And yes, it is. And so here we go. So let's take x minus 1 divided into x cubed plus 0x squared plus x plus 0. Right? Placeholders for any term that's not there. X times x squared is x cubed. Okay, so that would leave me with the following expression if I multiply through. Okay, I do a little subtraction. That gives me x squared. I'm going to drop down an x. And I'm going to divide in. So x goes into x squared x times. And I multiply through. So it'll give me x squared minus x. Okay, I'm going to run out of some space here, but we'll see what happens. It looks like I get a 2x. Okay, if I subtract. Now, I don't need this 0, but I can rewrite it like that. And since, let's see now, x goes into 2x 2 times. Okay, that would actually, let's clean this up. So I'd have 2x plus 0, and imagine I multiply through. That would be a 2x and a minus 2. So I'm going to subtract. Let's see what we get left over is a 2. Therefore, this integral here would be equal to x squared plus x plus 2 plus 2 over x minus 1 dx. Okay, so I'm able to integrate this. That would be x cubed over 3 plus x squared over 2 plus 2x, and then of course the integral of this last expression here, as you can probably anticipate, you could use the u sub if you want. It's going to be plus 2 times the natural log of x minus 1 plus c. All right, there you have it. That's a pretty awesome example. I'm going to leave number 5 for you, and actually number 6. Number 6 is going to require a BC technique. Okay, that technique is not one, I think I spelled technique right, yeah. That's not one that you can do in AB, so yeah, avoid that one. You're not going to be held responsible for that, but do number 5 on your own and check back with your teacher. All right, guys, we'll see you in the next video.